Alright, 9.3 Taylor's theorem. So up to this point we've been using Taylor's theorem, we just haven't used its entire theorem. So when we're generating Taylor polynomials and Taylor series, we're using part of Taylor's theorem, but there's also the second part of it. It's the remainder theorem, or remainder part of it. So Taylor's theorem with the remainder. So we're going to talk about that in 9.3. A lot of the problems are going to be similar to ones that we've had already. But a lot of my conversation is going to be about the remainder part. Like, what is the remainder and what does it represent? So, just out of the notes here, it says, if we have all of the terms in a series, the error is 0. Okay, so if it goes to infinity, we have every single one of them, there is no 0, or there is no error. If we have some of the terms, the error is the stuff that we did. The more terms, obviously, the less error will occur. So this is kind of this is example 2 out of 9.3. There aren't a lot of scenarios where we have this, but it's kind of a unique case. So we're supposed to find a formula for the truncation error if we use this. So we can see that our multiplier, our r, is x squared. Our first term is 1, and this is not the complete series because it ends at x to the 6. So the error will be everything after it ends at x to the 6. General formula, initial, which is 1 over 1 minus x squared. So that's the formula, and the interval is -1 to 1. That's given to us, but we could see, if we put x squared between -1 and 1, you square root it, you're still going to have -1 to 1. Okay, so the error would be everything afterwards, which would be x to the 8th, x plus x to the 10th, and so on. So if we wanted to say, what is the error, and can we write it in some sort of a expression, well, we could just say, well, that's my initial, and we're still multiplying by x squared every time, so it'd be x to the 8th over 1 minus x squared. So that would be the error. It's every term after the x to the 6th. So it says the error itself is a geometric series. Like I said, they aren't always going to be that way. Most of them are not. So Taylor's formula, we've been doing this already. That's like when we do the initial coefficient divided by n factorial times x minus a to the nth. So that's all things that we've done, but then there's an r sub n of x, which is the remainder part of Taylor's formula at the end, and that represents basically the next term. So if this is the nth derivative of a over n factorial times x minus a to the n, the remainder part of it looks the same. It's the n plus first derivative, which you see here, over n plus 1 factorial times x minus a to the n plus 1. So what's different is we've got a c here instead of an a here, but it's basically the next term. It's just using a different value. It's not a, it's now c. So what is c? C is some number between a and x, which the x's will be an interval that will be provided for you. I'll talk more about that later on. And c is the number in our interval that represents the maximum value of the n plus first derivative. Really confusing. Okay, so hopefully after a couple examples it'll make sense. So if the remainder, or the error, so that this term right here, if it approaches 0, as we get more and more terms as n goes to infinity for all x in there, then we say that the series generated converges to the function. So if this error is going to get smaller and smaller and smaller and smaller with every term and eventually go to 0, then we know that the series itself is going to converge to whatever function it is. down to 0. All right. So example 3. All right. Yeah, this is example 3 out of the book. Okay, so we're going to prove that sine x is this. Okay, so if it is that, then the error has to be 0 as n goes to infinity. Okay, so let's take a look at what the error is going to be. Well, the error is the n plus first derivative of c over n plus 1 factorial times x minus a to the n plus 1. Okay, so we can see that our a here is 0 because it's not x minus 2 or x minus 3 or whatever, it's just x. So that becomes just x to the n plus 1. The n plus first derivative, so just looking at the characteristics of our function, sine x. The derivative of sine x is cosine, derivative of cosine is negative sine, and so on. So whatever result with a derivative is never going to be greater than 1 or less than negative 1. So with every derivative we do, it's still going to remain between negative 1 and 1. So the largest that could possibly be, like if I found the 10th derivative of sine x, it's never going to be more than 1 or less than negative 1. Okay, and when we do the remainder or the error, we just do absolute value because we don't care if it's a positive error or negative error. So we just do an absolute value over the whole thing. So this n plus first derivative of sine x, we're just going to call that 1 because that's the biggest it could possibly be. And we're looking to bound it from above. Like what's the biggest the remainder is going to be? Then we know that the remainder is going to be less than or equal to that. So the n plus first derivative, we're just going to replace with 1 because it'll never be bigger than that. Over n plus 1 factorial times x to the n plus 1. So now what is this? What happens with x to the n plus 1 over n plus 1 factorial? Well, so x is just some number. So think of it as an exponential over a factorial. So if it's like 2 to the n plus 1 over n plus 1 factorial, which one is more powerful or dominant? So actually a factorial will outstrip a power expression, which is basically an exponential once you replace your x with a number. Okay, so it's more powerful, or it goes to infinity faster on the bottom. So this, as n goes larger and larger, approaches infinity, will become 0 because it's more dominant on the bottom. So remember, this represents the for sine x, and if we say that this goes to 0, then we know that the error will eventually go to 0, and if the error goes to 0, then we can safely say that sine x is this series when n approaches infinity. Alright, day 2, but we'll just keep on rolling because we're only 7 minutes and 40 seconds into it. Number 27 from your assignment. So 27, consider the initial value problem. We've got the derivative is equal to e to the negative x squared, and it has initial value x equals 0 and y equals 2. So the question is, can you find a formula for the function y that does not involve any integrals? Alright, so we have a differential equation and an initial value problem. If we're going to solve for y, we have to integrate or find antiderivative. So can we do it? No, you have to involve integrals. So typically we would find the antiderivative, and toss in a plus c, and then plug in 0 and plug in 2, and we get our y. The problem with that is we don't know the. Okay, nobody knows it, even though, you know, according to the calculus and fundamental theorem, it has to exist. We just haven't figured it out yet. Okay, so we're going to get around it. Part B says, can you represent y by a power series? So this is dy dx is right there. So y would be like the integral of that. So e to the negative x squared knowing that e to the x is this series, we can plug in negative x squared into all of the x's. So you end up with 1 minus x squared plus x to the fourth over 2 factorial, and so on. So we're replacing all the x's with negative x squared. And remember, that's the derivative, or dy dx is equal to that. So we have to integrate it. So I changed them to t's because we're going to integrate it from 0 to x. Because you find the antiderivative, then you just plug in the x afterward. You don't want to overuse the variable x. So they're t's, and then you can make them x's after you evaluate it from 0 to x, because we're going from 0 to x. Okay, so there's our differential, and then we integrate it term by term, antiderivative, and so on. And we're going from 0 to x, and we replace it, and now remember the value when x is 0, y is 2. So you can make them all 0. You're going to end up getting a constant plus 2 at the end. So even down to the nth term, the antiderivative is right down here, and we have a series, the antiderivative or integral of e to the negative x squared with an initial value 0, 2. So we never found the antiderivative of this, but we got around it by representing it with a power series. C says, for what value of x does this power series actually equal to what function y? Give a reason. Okay, so our initial e to the x, it kind of starts there. It's given that the interval of convergence is from negative infinity to infinity. Okay, so that goes for e to the x, will work for all x values. When we integrate it, it does not change the interval of convergence. That's Theorem 2, page 464. So integral of e to the so if we replace it with negative x squared, it doesn't change the interval. If you integrate it, it doesn't change the integral. So interval. So it's good for all real values of x. All right. Finding that the maximum error, and I've seen these every few years. These have been on the AP exam, so I've seen it on a free response question. It was on there maybe 3 years ago. So the Maclaurin series is for natural log of 1 plus x is this. That's right out of your book or on your Maclaurin series sheet. So what's the largest error which might result from using the first 3 terms? So we're just going to do the first 3 of this series to approximate natural log of 1 plus x. So how close is it? Like, is this a good representation of natural log of 1 plus x? How good of a representation is that, assuming x is between 0 and 1? Okay, so if we figure out the maximum error in that interval, we know how close this actually is, or at least we know it'll be within that amount. Okay, so the error, or the remainder term, or remainder theorem, is the n plus first derivative of c, and we're going to have to figure out what c is, over n plus 1 factorial times x to the n plus 1. Okay, it's Maclaurin, so it's not x minus a number here, it's just x to the n plus 1. Okay, so we are doing the first 3 terms, so that means we're going to have to do the 4th derivative, or 3 plus 1, 4 factorial. It's going to be x to the 4th, and it's going to be the 4th derivative on top. Okay, so the 4th derivative of natural log of 1 plus x is this. So that's what the 4th derivative looks like. We're trying to find the maximum magnitude of a y value. So we don't care if it's positive or negative. What's the farthest it will be from 0? So that in this interval from 0 to 1, it occurs right there at 0. Okay, so that means c is going to be 0. So our maximum of our fourth derivative from 0 to 1 is whatever y value that is in the absolute value of it. Okay, so looking at the formula here, this is my fourth derivative, and we're going to plug in 0 for c, and we end up getting negative 6, so absolute value is 6 over 4 factorial is 24. So 6 over 24, we end up getting 1/4. And then what is the x that we choose? So the x is in the interval, the largest value that could, what's the largest number in that interval? So in this case, it's going to be 1. Okay, so our interval is from 0 to 1. So again, we're trying to find the maximum of that, maximum of that. So it'll be 1. And its absolute value. So I could say it's always this, you know, if our interval is from A to B, we'd always choose B, but that's not true because we could be going from -2 to -1. And since it's absolute value, then it would be -2 would be our x. But think of this as the largest number in our interval. Okay, so according to the remainder theorem, once we simplify 6 over 24 times 1 to the 4th, the maximum would be 1/4. Okay, our error will not be more than 1/4. Okay, so if I wanted to take a look at what the error actually is, I could graph what our function is that we're approximating minus the actual function, and that would give you the error. So how far apart are they? Just do one minus the other one. Okay, so if I look, there's my natural log of 1 plus x minus my 3-term polynomial, and subtracting them, my window is from 0 to 1, and my y min is -1/4, and my y max is +1/4. So according to our formula, we're saying that this will never be our remainder, or which is our error, is never going to be more than 1/4. So looking at the graph, that's what it looks like. So this is the most, at that point, looks like at 1, if I subtract the 2, that is what the error is at that point. And if I want to calculate a value at 1, my error is -1 or 0.14. So basically 0.14, which is less than 1/4. So it supports what we found out, that the error is going to be less than or equal to 1/4. Exploration, we'll probably do that when we're in class. Example 5 here. It must be out of the book. So same type of a problem. Actually the same function, natural log of 1 plus x. So we're doing 2 terms. So what is the maximum error for this 2-term polynomial for natural log of 1 plus x? We do have a different interval. We're going from -0.1 to 0.1. Okay, so we use our formula. Our error is our n plus first derivative of c, whatever that c is, over n plus 1 factorial times x to the n plus 1. Okay, so since we have 2 terms, we're going to have to do our third derivative. So first derivative, second derivative, third derivative is this. So if we look at the graph of our third derivative, I have a little sketch of it here. From -0.1 to 0.1, you can see that the largest magnitude is going to occur right here. It's furthest from the x-axis at that point. So our c is going to be -0.1. That's going to produce the biggest number possible. So when we plug in c, we're going to plug in -0.1 right there. Over n plus 1 factorial, so 3 factorial, times x to the n plus 1, so x to the third. So what's the biggest x that we're going to have? You could either do -0.1 or I'll just do 0.1. We're going to do absolute value, so it's going to be 0.1 to the third. So what is 0.1 in for c? Looks like I moved the factorial over here. This is going to do some number times 0.1, that's our x, to the third over 3 factorial. Once you clean all of that up, you get 4.6 times 10 to the negative fourth. And what does that mean? That means that our error in our interval from negative 0.1 to 0.1 has to be less than or equal to 4.6 times 10 to the negative 4 when we're representing natural log of 1 plus x with this polynomial. All right, thank you. You've been a great audience.